As we all know, chemistry is all around us and has a large effect on the Earth. Today, I'm going to talk about a real-life application of a non-biological buffer system and how it's keeping our ecosystems in equilibrium. As we already know, buffer solutions are able to resist changes to their pH after acidic or basic components are added to the solution. They are able to neutralize small amounts of strong acids or bases. However, this will only work within their specific pH range. Outside of this pH range or quantity, the pH will change and it will reach its equivalence point. Buffer solutions must consist of an acid-base pair that have the ability to neutralize small amounts of acids and bases. Talking about buffer systems has a great deal to do with acids and bases, so we might as well review them a little bit. Acids are proton donors that donate a hydrogen ion. They occur in aqueous solutions, they conduct electricity, taste sour, and they have a pH below 7. Bases, on the other hand, are proton acceptors. They also occur in aqueous solutions, they conduct electricity, they taste bitter, and their pH is above 7. As a review, to determine how acidic or basic a solution is, we take the concentration of hydronium in the solution and plug it in to the equation pH is equal to negative log of the hydronium ion. We do the same for bases with its hydroxide ion to find the pOH. We can then also recognize that the pKw is equal to the pH plus pOH, which is equal to 14. If we are dealing with weak acids and bases and we want to find the concentration of hydronium or hydroxide in solution, we must use ice tables and their corresponding acid or base ionization constants. We then use this value and plug it back into the pH or pOH equations discussed above. A shortcut, however, when dealing with weak acids and bases is to use the Henderson-Hasselbalch equation to find the pH by using the formula pH is equal to the pKa plus log of the conjugate base over acid. This image represents a lake that has been impacted by acid rain that formed as a result of smelting processes in the extraction of minerals. This lake lacked sediments that could buffer the acid, resulting in highly acidic water, damaging the ecosystem and biodiversity. This is an image of a lake that has had a natural buffer system within its sediments. These buffers were able to mitigate the effect of the acid rain and maintain a healthy ecosystem. Acid rain occurs when sulfur dioxide or nitrogen oxides are emitted into the atmosphere. These emissions can be natural through processes such as volcanism, or they can be human-induced, such as fossil fuel emission. The precipitation can actually have a pH as low as 3, which is pretty low. Natural water bodies contain sediments that can offset the negative effects of this acid rain. However, lacking these buffers acidifies the lakes and would eventually decrease biodiversity of many species. This is a set of equations that describes the processes of acid rain. In the first one, we see that sulfur dioxide would mix with hydroxide and create HOSO2. The HOSO2 would then combine with the oxygen in the atmosphere and create hydrogen dioxide and sulfur trioxide. This sulfur trioxide then combines with the water in the atmosphere, creating sulfuric acid, which comes down as precipitation and acidifies our lakes. We know that the surface of lakes react with atmospheric gases and the bottom of lakes react with sediments. Limestone is a type of calcium carbonate that is common in certain lakes. It acts as a natural acid-base buffering system. When acid and water react, let's say the acid is coming from acidic rain, the limestone is able to consume or add hydrogen ions to the water, which then buffers the pH. Limestone is a form of calcium carbonate. It only partially dissociates, thus acting as a proton acceptor or donor, which allows neutralization to occur. The first equation we're going to look at is equation 1, where calcium carbonate reacts with a hydrogen ion and forms a calcium ion and a bicarbonate ion. When looking at the sulfuric acid reaction formula, we saw that sulfuric acid is an acid that obviously has a lot of hydronium ions and hydrogen ions available. So if more protons are added to the lake water and are available from the acid rain, the bicarbonate ions that are formed in equation 1 above can actually undergo a second reaction. So bicarbonate ions plus hydrogen ions, which are still available from the acid rain, then creates a neutral atom, a neutral molecule, So for every 1 molecule of calcium carbonate, 2 protons from the acid rain are used up, making the calcium carbonate double as powerful. However, no buffer is invincible. Eventually, it will reach its buffer capacity. Smelting processes from the extraction of iron copper ore has resulted in sulfur dioxide being released into the atmosphere, eventually falling into lakes as acid rain. What are the effects on a lake ecosystem if 0.0015 moles for every 3 liters of acid rain falls into a solution that is 0.56 molar calcium carbonate and 0.07 molar bicarbonate for every 12 liters? On this page, we're going to determine the pH of the acid rain. The first thing we're going to do is we're going to look at the overall sulfuric acid equation that we found on an earlier slide. We see that it breaks up into these components, which then further breaks up into these components. This allows us to get an overall equation by canceling out the HSO4 minuses to get sulfuric acid yields 2 hydrogen ions and an SO4 minus ion. We were given the moles of the sulfuric acid to be 0.0015 moles. We can then use mole ratios to find the moles of the hydrogen ion by multiplying by the coefficient of 2, which we found here, over 1. This gives the moles of hydrogen ion to be 0.003 moles. We can then plug that into the concentration equation to find the concentration of the hydrogen ion to be 0.001 moles per liter. We can then use the hydrogen ion as the hydronium in the pH equation. Using that, we find the pH is equal to negative log of 0.001, which eventually gives us a pH of 3, which is pretty acidic. We are now going to determine the initial pH of the calcium carbonate solution, which is where the acid rain is falling into. The question gave us the value for the Ka, which is 5.01 times 10 to the negative 11. Plugging that into the pKa equation, we determine that the pKa is equal to 10.3. Using that pKa value, we can plug that into the Henderson-Hasselbalch equation and determine that the pH is equal to 10.3 plus log of the concentration of the calcium carbonate, which is 0.56, over the concentration of the bicarbonate, which is 0.07. This gives us an initial pH of 11.203, which is very important. Previously, we calculated the pH of the acid rain and the pH of the limestone rock. But what happens when the acid rain enters into the lake ecosystem? That's what we're going to find out here. We're going to want to find the initial moles of the calcium carbonate and the bicarbonate. We do that by using the equation N is equal to C times V. And we use the volume, which was given to us in the question, of 12 liters. So the initial moles of calcium carbonate is 6.72 moles, and the initial moles of the bicarbonate is 0.84 moles. Also, we were able to calculate in an earlier slide that the moles of the hydronium in the acid rain is 0.003 moles. So as that acid rain is entering into the ecosystem, it's actually being subtracted from the calcium carbonate and it's being added to the bicarbonate. So we're going to subtract the 0.003 moles from the 6.72 moles to get 6.717 moles, and we're going to add the 0.003 moles to the 0.84 moles to get 0.843 moles. Then we're going to want to find the final concentration using C is equal to N over V and the new final moles. So the final concentration of the calcium carbonate is 0.559 moles per liter, and the final concentration of the bicarbonate is 0.0702 moles per liter. We can then use those newfound final concentrations in the Henderson-Hasselbalch equation to denote that the final pH is 11.200. So, Even though a strong acid such as sulfuric acid was added into a lake ecosystem, the limestone rock was able to buffer it and resulted in a very slight pH change. So the initial pH we found was 11.203 and the final pH was 11.200, showing that buffers are able to mitigate the effects of acid rain. Throughout this presentation, I hope you realize how important buffer systems are to our environment. If freshwater ecosystems lacked calcium carbonate buffer systems, organisms living within the ecosystems would die. They're able to keep ecosystems in balance by maintaining food webs and making them less vulnerable to environmental stresses. I hope the application of buffer systems to our lake ecosystems have helped you better understand chemistry and acid-base equilibria.